Think about the last time you learned something about ancient mathematics. Maybe it was in school. Maybe it was a documentary. And I'm willing to bet they told you the story starts in Mesopotamia around 3000 BCE. Maybe Egypt around the same time. Then the Greeks came along, formalized everything. Thales, Pythagoras, Euclid, and we got the mathematics we use today. That's the story everyone knows. That's the story taught in virtually every school in the Western world. Here's the problem with that story. It is incomplete. Not because information is missing. It's incomplete because entire civilizations, entire continents, and tens of thousands of years of human mathematical development have been systematically erased from the historical record. The oldest mathematical artifact ever discovered isn't in Mesopotamia. It's not in Egypt. It's in southern Africa. A piece of bone with 29 deliberate notches carved into it, over 43,000 years old. 40,000 years before Mesopotamia even existed as a civilization. There are other artifacts, multiple bones showing mathematical thinking, evidence of geometric cognition going back 70,000 years, all from Africa, all deliberately excluded from the standard historical narrative. This isn't hidden knowledge. These artifacts exist in museums. They've been excavated, carbon dated, and studied by researchers worldwide. And yet most people have never heard of them. So why weren't you taught this? That's the question we need to answer first. The answer has to do with historiography. How history gets written, what counts as evidence, whose records survive, and what achievements get recognized as significant. When historians write about ancient mathematics, they privilege written records. Mesopotamia gives us clay tablets with cuneiform numbers. Egypt gives us papyri with calculations and geometric diagrams. Greece gives us philosophical texts. These are explicit, durable, relatively easy to interpret. But mathematical thinking didn't begin with writing. It began with human cognition, with observation, counting, pattern recognition. Those things leave traces in archaeology, but they're different kinds of traces. A bone with notches, geometric patterns carved into stone. These require interpretation, which makes them easier to dismiss as not really mathematics or just primitive counting. When archaeologist Denise Schmant-Besserat discovered small geometric clay tokens at Tepe Gawra in Iraq dating to 4000 BCE, they were immediately recognized as an accounting system for tracking grain and livestock. But a bone with systematic notches found in Africa? That required decades of debate before anyone took it seriously. The difference isn't in the artifacts, it's in whose intellectual history we're willing to recognize. African mathematical traditions were often transmitted through oral knowledge and practical techniques that didn't require permanent documentation. The fact that oral tradition doesn't leave scrolls and tablets doesn't mean the knowledge was less sophisticated. It means we need different frameworks to recognize it. If we grant Babylonian clay tokens the status of proto-mathematics, we can grant African notched bones the same recognition. The playing field needs leveling. Let's go back 70,000 years. Blombos Cave on the southern coast of South Africa. Inside this cave, archaeologists found pieces of ochre, a red mineral pigment, with geometric patterns engraved into them. Not random scratches. Systematic, repeating geometric designs. Cross-hatching, parallel lines. Organized sequences that appear across multiple pieces of ochre with remarkable consistency. These pieces are between 70,000 and 100,000 years old. This isn't formal mathematics. No equations, no calculations, but it's the moment humans learn to think in patterns. The birth of abstract geometric thinking. Creating a geometric pattern requires you to see that lines can be arranged systematically, that certain arrangements create repeating structures, that you can plan that structure in your mind and execute it with precision across multiple objects. That's not instinct. That's abstract reasoning. These exact patterns are the foundation of triangulation technology. Every GPS system, every mapping app, every Find My Location feature uses this 70,000-year-old African mathematical insight. And these repeating patterns that scale at different sizes? That's fractal geometry. The same mathematical concept is now used in image compression, computer graphics rendering, and modeling natural phenomena. When you compress a photo on your phone, you're using fractal mathematics. The people at Blombos Cave were laying the mental architecture that all mathematics and modern technology would eventually be built upon in Africa. At the very beginning of human abstract thought, fast forward to the Lebombo Mountains on the border of South Africa and Eswatini. In Border Cave, between 1970 and 1975, South African archaeologist Peter Beaumont discovered a baboon fibula with 29 deliberate, evenly spaced notches carved into it. Radiocarbon dating places the artifact between 43,000 and 42,000 years old. Not decoration. Intentional cuts with clear purpose. But what were they counting? Peter Beaumont himself noted that the bone resembled calendar sticks still in use today by Bushman clans in Namibia. In 1987, mathematicians Jonas Bogoshi, Kevin Naidu, and John Webb published the first formal analysis of the bone, identifying it as potentially the oldest mathematical artifact known. They argued that the deliberate, evenly spaced notches demonstrated systematic counting, mathematical thinking made tangible. In 2004, astronomer and science writer David Darling expanded this interpretation in the Universal Book of Mathematics, proposing that the Lebombo Bone's 29 notches may have been used as a lunar phase counter, in which case, African women may have been the first mathematicians, because keeping track of menstrual cycles requires a lunar calendar. But there's another possibility. Maybe both theories are valid. Maybe ancient peoples understood the connection between lunar and menstrual cycles and tracked both simultaneously, recognizing how patterns in the sky mirror patterns in the body. The 2012 study by archaeologist Francesco Derrico and colleagues, published in the Proceedings of the National Academy of Sciences, provided additional confirmation. Their analysis of organic artifacts from Border Cave demonstrated that inhabitants between 44,000 and 42,000 years ago used notched bones for notational purposes, deliberate record-keeping that represents abstract thinking and mathematical cognition. One intriguing detail is the choice of baboon bone. We cannot trace symbolic meanings back 43,000 years with certainty, but it's worth noting that in later African cultures, baboons held powerful lunar associations. In ancient Egypt, Hamadryas baboons were sacred to Thoth Khonsu, the moon god, and they were depicted with lunar crescents on their heads. Whether such symbolic connections existed in the minds of Border Cave's inhabitants remains uncertain. The gulf of time is too vast. Perhaps it was simply practical. Baboon bones were available, durable, and the right size. We cannot say for certain. It's also worth noting that the bone is broken at one end. 29 notches survived, but we don't know if there were more. The full count may have been higher. Even so, what we have is enough to establish something profound: systematic counting, applied observation, and the creation of tools to record patterns, the foundational elements of mathematics. The Lebombo bone sits in the South African Museum. You can see it. You can study the notches. And it predates everything you were taught about where mathematics began by 40,000 years. In 1950, Belgian geologist Jean de Heinzelien was excavating near Lake Edward in what was then the Belgian Congo. He found the remains of a small fishing community buried under volcanic ash around 20,000 years ago. Among these remains was another bone, another baboon fibula, approximately 10 centimeters long, with a piece of quartz still attached, possibly the tool used to engrave it. This became known as the Ishango bone, and it shows something extraordinary. The bone has 3 columns of notches, 168 marks total, organized into deliberate patterns that modern mathematicians still debate. The central column shows doubling and halving, a clear arithmetic pattern. It begins with 3 notches, then doubles to 6, then 4 notches, which doubles to 8, then 10 notches, followed by 5, which is 10 divided by 2. This isn't random. Someone understood multiplication and division by 2, the exact same principle ancient Egyptians used thousands of years later for their multiplication system. This doubling pattern? It didn't disappear. 20,000 years later in Ethiopia, merchants developed a multiplication method that breaks numbers into powers of 2, doubling and halving.
To multiply 11 by 15, Put the numbers into 2 columns. Keep halving the number on the left, ignoring all fractions. 11 becomes 5, becomes 2, until you reach 1. In the other column, you double. 15 becomes 30, becomes 60, becomes 120. Whenever an even number appears in the halving column, ignore the row. Group the remaining beans in the doubling column together and count. You get 165, the perfect answer.
When you repeatedly double and halve numbers, you're breaking every number down into combinations of 2. That insight is binary code, the exact system that runs every computer, every smartphone, every digital device you've ever touched. Binary works with just 2 symbols, 1 and 0. Each position represents a power of 2, and the symbol marks whether that power is present, marked as 1, or absent, marked as 0. The Ishango bone isn't just ancient. It's the cognitive ancestor of the technology you're using right now. The left column is where scholarly debate intensifies. Groups of 11, 13, 17, and 19 notches. Those are prime numbers. Specifically, every single prime number between 10 and 20, listed in consecutive order. Mathematician Claudia Zaslavsky, who spent decades studying African mathematics, argued that this shows someone understood that primes had unique properties, that they were fundamentally different from other numbers. Other scholars remain more cautious. They point out that organizing numbers into groups of 10 to 20 could produce these groupings through other systematic principles. Perhaps astronomical observation, perhaps lunar calendars, perhaps organizational schemes we haven't reconstructed. Alexander Marshak, the renowned American anthropologist who documented the earliest calendars and notation systems, believed the whole bone was a 6-month lunar calendar for tracking moon phases across an extended period. Here's what matters. Scholars debate the sophistication, but no one debates the mathematical thinking. The patterns exist, they're intentional, they require explanation. We're debating whether someone understood prime numbers or was tracking complex astronomical cycles. Either way, it's sophisticated mathematical cognition in Central Africa 20,000 years ago. The Ishango bone currently sits in the Royal Belgian Institute of Natural Sciences in Brussels. A small object representing something enormous. Physical proof that sophisticated mathematical thinking existed in Africa when the rest of the world was tens of thousands of years away from comparable systems. These artifacts are interpreted more skeptically than comparable evidence from other regions. That skepticism isn't scientific rigor, it's historiographical bias. The standards applied to African mathematical artifacts would disqualify half of what we accept about Mesopotamian and Greek mathematical development if applied equally. The story you were taught, that mathematics began in Mesopotamia around 3000 BCE, that it was formalized by Greeks centuries later, that story was fundamentally wrong about the timeline and origin point of human mathematical development. Africa is not just the cradle of humanity. It is the cradle of mathematical consciousness itself. And that mathematical tradition didn't freeze in the past. It evolved, diversified, became embedded in culture, and now powers the modern world. What we've examined today is remarkable but incomplete. We've seen evidence from tens of thousands of years ago. But we haven't seen how this mathematical thinking developed and formalized as African societies grew more complex. This story doesn't end with ancient bones. It continues, it develops. Mathematical thinking becomes connected to architecture, astronomy, engineering, and social organization. In our next episode, we're moving north along the continent, from 20,000 years ago to 5,000 years ago, to a place called Nabta Playa in southern Egypt, just south of where ancient Egyptian civilization will emerge. There, we'll find a stone circle complex that predates Stonehenge by 1,000 years. Nabta Playa is the bridge between the deep mathematical traditions we've examined today and the formalized systems Egyptian civilization will develop. It shows how mathematical thinking moved from individual tools to collective monuments. The mathematical revolution didn't begin in Mesopotamia. It began in Africa. We'll see you in the next episode.